So today we're going to finish up section 4.4. We're just going to do 3 more examples. And then we're going to start 4.5 and we'll finish 4.5 on Friday. All right, so what we're going to do now is we're going to continue with the examples we were working. So we talked about reference angles, and then we started doing examples where we applied them. And we looked at one where I gave you a coordinate point for the end of the terminal side, and we figured out how to get the 2 sides of the triangle. Then we looked at one where I gave you the equation of the line for the terminal side, and we saw how to get the 2 sides of the triangle off the slope. So now we're going to do 3 more problems, and you're going to see in each problem we give you a new way of telling you how to figure out where the what quadrant you're in, right? But once you're in that quadrant, the background calculations are pretty much identical. Solve for the third side using the Pythagorean theorem, and then list out the 6 trig functions that go with it. So just to make things a little easier in writing today, if in the problem I use the notation just trig of theta, that means we're going to find all 6 trig functions. So let's look at an example. All right, so we're told to find all 6 trig functions of an angle theta if theta is in quadrant 3 and the terminal side is perpendicular to y equals negative 13x plus 1. So rather than actually giving you the equation of the terminal side, we've told you that the terminal side is perpendicular to this line. So there's sort of 2 approaches you could start with this problem. You could deal with the quadrant first, or you could deal with the line first. So if you just went ahead to quadrant 3 and drew the triangle, that's fine, but you're still going to have to deal with the line in order to get the sides of your triangle out. So one thing you want to make sure that you remember whenever we're using lines, right, to be our terminal side or represent them, all terminal sides of angles, right, they start at the origin and go out. So that means any line that you're dealing with has to go through the origin. So we actually know that the line we're looking for is going to have a y-intercept of 0. Because it's got to pass right through the origin, right? Furthermore, because they said perpendicular to this line, well, we know the slope right here is negative 13 over 1, so we flip the fraction and then multiply by negative 1. So it would be positive 1 over 13. Well, it's perpendicular slopes are negative reciprocals. So you flip it and then multiply by negative 1. So it would have been negative 1 over 13, and then when you multiply by negative 1, you're going to get positive 1 over 13. So the equation of the line we're looking at is just 1 over 13 times x. The b is 0. So that's just a positively sloped line that goes through the origin. So if you missed the quadrant 3 at the beginning, well, this line would actually go through quadrants 3 and 1, right? Because it's a positively sloped line. And so we have to know that we're just going to isolate to quadrant 3. So the triangle we're going to have is going to look like this. So the angle theta, right, is started in standard position. So it goes all the way around to that terminal side. But we've talked about on Monday, right, we could just deal with the triangle in that quadrant. The reference angle is fine, okay? Now, in order to label these sides, right, we said, well, the slope of the line is rise over run. So we see that it's going to have a height of 1, right, and a base of 13. But we're in quadrant 3. So even though this has got value 1, this has got value 13, x's and y's are negative in this quadrant, so you would have to make them negative. And it still works, right? Negative 1 divided by negative 13 is positive 1 over 13. So you want to make really, really careful that you're not just blindly taking the numbers, that you're verifying the signs of those numbers match up with what quadrant they're in, okay? So now we need to get the third side. And so we're going to use the Pythagorean theorem to do that. So negative 1 squared plus negative 13 squared will equal r squared. So 1 plus 169 is r squared. So the square root of 170 is r. This isn't a perfect square, so you just leave it as the square root of 170. So that's your hypotenuse. Now that you have your hypotenuse, we can list our 6 trig functions. So for the first 3, right, we just used SOHCAHTOA to figure this out. So sine is opposite over hypotenuse. So it's negative 1 over square root of 170. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent, but negative 1 over negative 13 is just 1/13. So if your terminal side is a line, like this was, tangent of the angle should come back as the slope of the line, because tangent's opposite over adjacent, right? And the slope is y over x, change in y over x. So tangent is going to be the slope of the line. It should come right back, right? Then, since these are the reciprocal identities, right, we just flip each fraction. Any questions on this? All right, so let's look at another one. So what quadrant are we in? Second. So t is between pi over 2 and pi, right? So this is 0, there's pi over 2, there's pi. So one of the ways we can give you the quadrant is we can give you the bounds on the quadrant and tell you that the angle is somewhere inside of that. So basically we told you that the angle t is somewhere between pi over 2 and pi. So that means, right, we can draw our terminal side here. So this is actually, right, angle t, but when we draw our triangle, this is the reference angle. I should have really been t sub r, but there's the reference angle within that triangle. So that's what they're doing. So we can give you an interval to describe the quadrant, okay? So now what we've done is we've just given you 2 of the sides by giving you one of the 6 trig values. So if you know that sine is opposite over hypotenuse, right, then the opposite side we can give a length of square root of 5, and the hypotenuse we can give a length of 12. So square root of 5 is going to go here, 12 is going to go here, and now we're missing the x value. So you want to be careful when you're using the Pythagorean theorem, because up till now, the way we've done this problem is we've had the legs and not the hypotenuse, right? Now we've been given the hypotenuse, but we're missing one of the legs. So make sure you're really careful that you're putting the right piece in the right order when you're doing the Pythagorean theorem. So in this guy, right, it's going to be the square root of 5 squared plus x squared equals 12 squared. Square root of 5 squared is 5 plus x squared equals 144. X squared equals 139. And x is actually plus or minus the square root of 139. Now when we solve for the hypotenuse of the triangles, we were just grabbing the positive square root because that value always has to be positive. Only the legs are going to take on positive or negative numbers because of the way the coordinate system's set up, right? But when you're solving for one of the legs, you're going to produce two answers, and you have to make sure you put the right one in the right place. So which one do I want?
The negative.
The negative, right? So x is going to be negative, right, square root of 139. Now, it seems kind of silly, but this is one of the things we do, and there's actually kind of a reason for it, to ask you to return all 6 trig functions when we actually already gave you one to start with, okay? And so the very first thing that you would be asked to do if this were on ALEKS or any other computer system is you would have to give back, it should just be the same value of sine you were given, square root of 5 over 12. But it's actually nice because you can, I recommend you pull sine out of the triangle, and that's a good check on yourself of, oh, if your value for sine out of your triangle isn't matching the one they gave you at the beginning of the problem, maybe you drew in the wrong quadrant, right? Maybe you labeled the sides wrong, right? So the very first thing when you use SOHCAHTOA, right, is we'd say, well, opposite over hypotenuse, right? This checks out. So we at least got that right. Cosine is going to be negative square root of 139 over hypotenuse. And tangent is going to be the square root of 5 over the negative square root of 139. So that's a perfectly acceptable answer, but sometimes, since we have a radical over a radical, an equivalent answer would be to just combine the whole fraction under the one single radical. So if you're typing, right, it might be a little more cumbersome to put a radical over a radical than it would be to just put the fraction and take the square root of the whole fraction. Right? So then the rest of these are reciprocal identities. So we just flip. So what if I gave you the same problem, but I took the interval away, and I said, instead of finding all 6 trig functions, I just said, suppose sine is square root of 5 over 12, what is cosine of t? All right? So if we didn't give you the interval, then similarly to like a quadratic has possibly up to 2 solutions, right? If we didn't give you the interval, well then what that would mean is there are 2 possible values for cosine. Because if sine is positive, right, there are 2 quadrants where sine is positive. Number 1 and number 2. So you would draw triangles in each of these quadrants. Now the nice thing is due to symmetry, the heights are the same, right? The hypotenuses would be the same. But the difference would be you would put negative square root of 139 over here and positive square root of 139 over here. So you would just return 2 possible answers. You'd say, well, cosine's either negative square root of 139 over 12 or positive square root of 139 over 12. So if we don't isolate it down to a single quadrant, you would just go into all the quadrants where that condition holds and then give the corresponding cosines back. So you could have situations where we just ask you to do a single trig function and there's more than one answer. All right? If I said something like sine I could say something like the absolute value of sine of theta is 1/2, right? Well, absolute value is going to always produce the positive answer. But what that really means is there's an angle that's going to give you a positive 1/2 for sine, and there's an angle that would give you a negative 1/2 for sine, right? But either one of those, you take the absolute value, you're going to get positive 1/2. So in that situation, what we're really saying is, right, sine could be either 1/2 or negative 1/2. So that means you would have to put triangles in all 4 quadrants because there's 2 locations where it could be positive 1/2, 2 locations where it could be negative 1/2. But it's the same triangle in all 4 quadrants. So you would just use the x and y, what we know about the signs in those quadrants. So be prepared to start seeing some problems where there's actually more than one right answer. But you're still going to have symmetry, and you're only going to have to do the Pythagorean theorem once, because the lengths of the sides will be the same in all 4 quadrants. It's just the sign in front of the numbers could change. All right, so let's do one more of these. Since we know this is coming, let's go ahead and do this too. So where is tangent negative? Quadrant 2 or 4, right? In quadrant 1, everything's positive, so sine over cosine is going to give you a positive answer. In quadrant 3, everything's negative, so you're going to have negative over negative, right? So quadrants 2 and 4 are where tangent is negative. This is saying, well, right, so we're already here, right? And then this is saying, well, sine of theta for the same angle is negative. So whenever we have an inequality and we compare to 0, we're really saying positive or negative about something. So this is saying sine is negative. So if sine are the y values, sine's negative down here. So quadrant 4 is the only one where both of those things are true at the same time. Tangent is negative and sine is negative. If I had said sine is positive, we would have been in quadrant 2 because sine are the y values, and that would have been where they're both true, okay? So that means we're in quadrant 4. So here's our reference angle. The entire angle theta is in standard position and is actually all the way around here. So the other reason this matters is because if tangent is negative, right, you technically don't know if that's a negative 24 divided by a positive 7 or a positive 24 being divided by a negative 7, because we can move the negative sign from the numerator to the denominator. And sometimes on fractions, especially when they're typed, they'll actually put the negative sign right here next to the fraction bar, so you don't even know if it's in the numerator or the denominator. So what you want to do is you want to verify by the quadrant that you're in where to put the positive and the negative number. So if we were in quadrant 2, right, the y values would be positive, so it'd be positive 24, negative 7, right? But because we're in quadrant 4, Y's are negative, and X's are positive. So by just literally flipping the sign less than 0 to the sign greater than 0 would have moved you to a different quadrant and changed the sign of those two numbers. So that's why you got to be real careful and come up with like checks for yourself to make sure you're labeling stuff right. All right, so now we need to solve for the third side. So 7 squared plus 24 squared is going to equal r squared. 7 squared is 49. 24 squared is 576. So when you add those together, you get 625. And the square root of 625 is 25. So we actually get an integer. So now we can use SOHCAHTOA. So the opposite side is negative 24. Our hypotenuse is 25. The adjacent side is 7. The hypotenuse is 25. Opposite over adjacent, right? And that just returned the tangent we were given, so that's good. And then we flip to do the remaining 3. So one of the reasons that I was saying you can't just pull the numbers out directly is a lot of people, myself included, always put our negative signs in the numerator, right? When you're typing, a lot of times, the software puts it out next to the fraction bar. But if you're writing, you don't always see the distinction between the minus and the fraction bar, and it might look like one long line, right? So a lot of people always put it in the numerator because you tend to read a fraction from top down. And if you're dealing with a negative number, it's the same reason I always pull a negative number out front if I've got one, because there are rules that might change or be affected if you're working with a negative number as opposed to a positive number. And I just like that negative sign to just be loud and proud and right out front. So when you look at it, you're like, oh, this thing's negative, right? Sometimes if you leave it in the denominator and you start doing more problems, it's real easy for it to fall away and drop off and get lost. So that's just one of the reasons that I always bump it up to the top, just so I know that it is a negative quantity. And then if my work's being graded by someone, and a negative or positive matters, which like it does here, I want them to see right away whether I got a positive or a negative. Also, I've been personally burned by negative signs plenty of times, so I just kind of came up with little rules for myself. All right, so this is the end of 4.4. Does anybody have any questions? All right, so if you go back and compare all 5 of these examples, right, the underlying math computation was pretty much identical in all of these problems. It was how we described where to start, and every problem was very, very different. Okay? All right.